All right, let's move on to part C of question 1. So in part C, we're basically defining a new data structure called crummy quick union. Basically, everything about this structure is the same as regular quick union. The only change is that we're changing the implementation of the connect method. So that instead of appending the smaller tree to the larger tree, we're always gonna append the larger tree underneath the provided smaller tree. Okay, so let's take a look at part 1. In part 1, we're asking whether or not crummy quick union is implementing the disjoint sets interface correctly. So as a reminder, what an interface do in Java is that it simply specify which method we need to have, right? It doesn't specify the implementation of the method. So since we're not changing anything in terms of the quick union, other than the implementation of connect, we still have both the connect and is connected method, which means that we are implementing the interface correctly. So for part 1, we choose yes. In part 2, we're basically just asked the worst case runtime and best case runtime for the is connected method for crummy quick union. All right, so just as a quick reminder, let's look at what its connected method is supposed to do. So imagine we have this random tree right here, right? In the worst case, when we want to check if two nodes are is connected, for example, if we're checking node A and node B, what we need to do is that we have to traverse all the way back to the root node for both of them. And then we need to compare whether or not they're sharing the same root node. So when we're calling is connected on any of the leaf node or like on the last level, we will have to travel all the way back for a distance of height, right? So basically, when we're asked the worst case runtime of is connected, it's the same as asking what's the worst case height or the largest height that we might get from calling crummy quick union connected. But yeah, to find out what the worst case height could be for like a crummy quick union, maybe we can just walk through a simple example of connecting components. So for example, if we have like 3 nodes, 1, 2, 3, when we call connect 1 and 2, we get a component like this. However, if we call connect 3 and 1 after this, what's gonna happen is that we're simply gonna append the larger component under the smaller component. Notice how we are like ending up getting this like almost linear structure that looks like a linked list. So imagine if we just keep doing this, say if we have another node just hanging by itself called 4, when we connect 4 and say like 3, what's gonna happen is that we're appending the large component under the small component leading up to something that looks like this. So notice how like the height of the tree, or in this case, it looks like a linked list already. This worst case height is big O n, right? Because it's almost like a linear structure, and being the number of nodes we have. So basically, in the worst case, the runtime is the same as the worst case height, and then the worst case height is going to be theta n. All right, going back to the best case. So basically, when we call 2 nodes with like the is connected method, the best thing that can happen to us is that they're either like really close to a root node or they're already like a root node, right? So imagine if we call like is connected on these 2 nodes, basically we just need to step 1 step up to the root node, and then we can already check like whether or not they're sharing the same root node. So in the best case, imagine we're calling it on root nodes. In that case, we can simply just compare whether or not they're the same node. Okay, so I think this is